There we go. Woo! It worked. Okay. So go ahead and take a moment and write that down. Okay. Refraction. Reflection, we've already talked about. If I'm a photon of light and I hit something and I bounce off and keep going, that's reflection. Refraction is when light strikes something and instead of bouncing off, it goes through it. And it changes its direction when it goes through it. So when light coming from the window strikes the lens on my eyeglasses, the light goes through the glasses, but not in a straight line. It turns a little bit when it gets into my glasses. And then it turns a little bit again when it leaves my glasses and goes to my eye. And we can manipulate those turns, which is why glasses work, and they form an image. And if I take them off, you are all flesh tone smears. And honestly, I would have a very hard time without my glasses telling the difference between, you know, similarly built people. Like if Andy and Janine were to switch seats with my glasses off, I might not notice. But put them on, it's like, oh, it's you! And that's because light gets bent as it goes through my glasses. And that's called refraction. And refraction happens because of optic density, which is very close to regular density, but slightly different. It has to do with the different densities of the media and the shape of the boundary between them. So if I'm a photon of light and I run into a flat boundary between air and glass or air and plastic, and I'm coming at that boundary, I'm going to change a little bit as I go through the plastic. But if that boundary is bent, then the shape of the boundary is going to make me turn even more or less depending on how they shape that, which is why it's the shape of your lenses that controls your vision. And by changing the shape of the lenses, it changes the focus. On some light apparatuses like a camera or the projector, the shape of the lens doesn't change when we focus an image. We just change the spacing of the lenses, and you'll see why that works later. But right now we're going to talk about single lenses. So it's the shape and the density of the material that determines how much the light changes its direction and the path that it takes. So here's an example of a light beam striking this piece of plexiglass. If you notice, the light beam comes in and it does not continue in a straight line. It turns and it goes this way. And then when it leaves the plexiglass, it turns again and it goes this way. And so what happened is the light went from the medium of air to the medium of plexiglass. Change in density, change in direction. And so the light turns, keeps going in a straight line through the medium, and then when it goes from plexiglass back to air, it turns again. And what's cool is if this line is parallel with this line, then the beam of light here and the beam of light here will be parallel. It's like the light says I'm heading whatever direction this is. Roughly, see, that would be, that direction is 180, so this is maybe 200 degrees. The light is heading 200 degrees, it hits the plastic, and it's like, oh, detour, leaves the plastic, 200, and it keeps going in the same direction. And that's because we have the same change in density, from light to plastic and plastic back to light. If we shape these edges, now we're going to make this line and this line be different. And that's how we can like focus things with the lens, is by manipulating the shape and the density of the material, the optic density of the material. Okay. Here's some other examples. You played with this a little bit already in the color and light lab. You put a straw or a spoon in something, and it looks like the straw bends here because at this point, your eyeball is able to see just the plastic straw through the air. But at this point, you now see the straw through glass and then the air. So the straw bends here because you're looking through a medium change of air, glass, air to see the straw. So the straw looks like it bends. And then here at this point, the straw is actually still going in a straight line all the way down to the bottom of the glass. But now you're looking air, glass, water to see the straw, and the light is bent in a different way. And so it actually looks like the straw gets cut at the water line, and the rest of the straw is here, but it's connected, it's contiguous. What you're seeing is the difference in the refraction of air, glass, air straw, and air, glass, water straw. The different way that that image has been bent makes it look like the straw jumps. Similar thing with the spoon over here. Here we have a straight spoon, and it is still a straight spoon until it gets to the bottom. The wonky curviness here is because of the different density of the glass, not the different density, the different thickness of the glass. So the light is bent differently through this part of the image because the glass gets thicker. And then here again, the spoon looks like it jumps because now we're not going air, glass, air, spoon. Now we're going air, glass, water, spoon. And so the different refraction makes it look cut. Okay, but all of that is just examples of refraction of light. And we, again, use this in lenses all the time. If something looks fuzzy because your eye is deformed, my eye is deformed, Angela has deformed eyes too. It's okay, Jesus still loves us both. Now we can fix our eye deformation by looking through a lens that bends the light so that our deformed eye can make sense of it. Okay, so that's what this does. At some point, light can be bent so much by the boundary in the media that it reflects back into the first medium completely, and we call that total internal reflection. If you're a scuba diver or a snorkeler who spends a long time underwater, not just duck diving, then you might have noticed this. If you're down underwater and you look straight up, you see sky, because the light coming from the image of the sky goes through the water, hits your eye. But if you look at an angle to the surface of the water, you stop seeing an image above you, and you start seeing ocean again. The light that is striking your eye has come off of the ocean and actually bounced off the bottom of the surface of the ocean, and then is coming back to strike your eye, which causes something that divers call blue water disorientation. Because if you're diving in blue water, and there aren't like big landmarks for you, there's not some pile of rocks that you can anchor your orientation to and be like, oh look, there's the thing. If you're just blue water diving, which happens if you're spearfishing or those sorts of things, then there's no point of reference for you, and everywhere you look, it's blue. You see ocean, and you look up, and there's ocean, but that's actually the surface of the water. And then if you get all wonky and you look straight up and you see blue sky, your brain is like, all I see everywhere is blue. What's going on? And you can get totally turned around. And there are people who try to surface and they wind up swimming down. And people who, like, you can get totally turned around if you're blue water diving and they tell you to follow your bubbles, because your bubbles will always go up. So if you blow a bubble and the bubble goes that way, then that's up. Follow your bubbles and you'll get home, right? But that's caused by this phenomenon of total internal reflection, where you can look at the water and actually see a reflection off of the surface of it. And that's because the light gets bent every time it hits, and this blue line is the light leaving, right? And it gets bent, and it gets bent, and then there comes a point where you see the water, or you look up at the water, and the light gets bent so much that it gets bent right back into the water. So none of the light is leaving, okay? And total internal reflection, it screws up scuba divers, but it's good for fiber optic cables. Anybody have the new high-speed fiber optic cables at home? You have like awesome, powerful internet of like 200 megabytes per second or faster.
Ooh, by the way,
It's awesome.
Wanna invite me? Do you have?
No.
Oh, okay. Straight up.
But the reason it's so fast is because we're not sending electrical pulses through copper anymore.
Are they
We're
expensive?
sending light pulses through glass wire. And the light travels at the speed of light, and we can put much more information down that wire per second than we could put down a copper wire per second. And so this is cool because it's a glass wire, and the glass doesn't have to be coated with anything spectacular. It's just the edge of the glass going to not glass. And light coming down the tube, if the wire bends, the light just follows down the bent wire, the bent glass wire, because when it gets to the glass wire's frontier, it gets bent so much by the refraction that actually just goes right back into the wire. And the light signal travels wherever you want to bend this wire. The light signal travels down it, which is really cool because it's refracted so much that it's refracted back into the first medium, and it doesn't leave.
Are they expensive?
It costs the company a lot to put it in, and so they like to charge you more for it. But
What
I'm on
is it called again?
fiber optic. So this is an example of total internal reflection. Here I have, here the person who took this picture has a laser pointer pointing into an aquarium. And so the light comes in and then hits the surface of the water, and you would expect that the laser would come out and it'd be in the air. But because the boundary of water and air bends the light, it bends the light so much that it bends it right back into the water. So it doesn't leave the surface of the water. And the laser pointer line goes right back into the aquarium and comes out the glass, and you see the point of it down here. So refraction to the point that refraction turns into reflection. It's kind of cool. That's being bent back on itself. Give me a second to write that down. Okay, when you take physics in a couple years, you will get to do the math of refraction to a much greater degree, and we'll be able to see that the wavelength of light determines how much it bends when it changes medium. So when light goes from one medium to another and changes its direction, it does that as a function of its wavelength. So the shorter the wavelength, the harder a corner it takes. The longer a wavelength, the less of a corner it takes. And so because of that, white light that has all kinds of lights in it, all kinds of different colors in it, can be bent and scattered. So if we have white light striking a prism here, the red, which is a longer wavelength, is going to turn, but turn not as much as the violet, which is going to turn even more. And then in between, we get all the different color bands there. And the reason a prism works to spread out light is because the different colors turn different degrees when they cross the medium. And so they turn once here, and then they turn once again, and those two turns together make this dispersion of white light into its primary colors, its fundamental colors, okay? That happens in two common examples. We've already played with prisms once. Glass prisms like this, you can see that happening, and of course also we live in the what state? Hawaii is the what state? Okay, what else? Yeah, okay, no, our license plates have it. We're the rainbow state, hello. Yeah, so we live in the rainbow state, and rainbows are caused because water droplets do this too. If you were to picture here not just a glass triangle, but a spheroid sort of ball of water flying through the air, when white light hits the ball of water, it does the same thing, and we get a rainbow coming out of the droplets of water. And then if you are standing on the ground, and the droplets of water up there are casting a a rainbow of light as it comes out and falls, you will see a rainbow in the sky because all of the droplets of water up there are spreading out red light so that you see it up there. And then as that drop falls to you, it looks like it changes color, red, orange, yellow, green, blue, indigo, violet, and then you miss the dispersion and it looks like it's clear again as it falls. So the rainbow is not a thing. The rainbow is all of these droplets of water as they fall. The droplets look like they turn color as they fall. And just like a television looks like a picture to you because it's a whole bunch of little spots changing color, all the raindrops changing color as they fall look like a rainbow to you, right? Your brain interprets it that way. So, and of course, we as Christians can see that God intended this to be a message to us, and it's a symbol that God instilled to teach us about His mercy and His long-suffering and His patience with us. And it is our symbol, the rainbow, has been stolen, hijacked, shanghaied by the LBGT community. And sadly, they think it's their symbol, but it's wrong. And I've written on the sadness of the stolen rainbow, which isn't really the point now. But this is our this is a symbol to us that God chose to make that to have meaning to us. I don't think that it was the first rainbow ever when Noah's Ark landed, and that was the first time that water droplets dispersed light. I think water droplets had dispersed light before, but God then said, "Hey, when you see that, think of this," and so we do. So that's a very cool thing. Here we go. Lenses are the most common application of light refraction. And there are a couple of kinds of lenses. There are converging and diverging lenses. A converging lens, what does the word converge mean?
Together.
To come together. Good job.
Oh.
At 7:45, students from all over the island converge on Calvary Chapel at Honolulu in Aiea. Converge means to come from lots of places and wind up at the same place. So a converging lens takes scattered light and focuses it down onto one place. Okay? Converging lenses have to have at least one convex surface. What does the word convex mean? The opposite of concave, right? What does it mean though? Yes. Concave. Concave means there's a depression, a hole, like a cave, right? Convex sticks out. So a concave surface would be something like this, something that arches and out and sticks out or rises. That's convex. Concave is the opposite, where it goes down. If you look at a lens and it has at least one convex surface that sticks out, then it is probably being used to converge light, to take light from multiple places and focus it down to one point. The opposite is a diverging lens. To diverge means to scatter. So at 3:15, the students from Calvary Chapel, Honolulu, diverge from school out to the uttermost parts of the island. That means to scatter, to go away. And you can tell that a lens is diverging if it has a concave surface, right? It scatters light. It takes an image and blows it up all over the place. So here in the projector, we have diverging lenses because we're taking a very small image being produced by the LCD displays behind the lens, itsy bitsy image, and we're blowing it up to much larger sizes, and that's the job of a diverging lens. It scatters the light, makes a bigger thing out of the little thing that it's given. Okay? Versus our eyeglasses, which are converging. They take scattered light and they focus it down to a point. So you can see that my glasses are taking a very large image coming at it, and are able to take that light and bring it down into a small space, which is why you see a little bright region behind my glasses, because they're taking diverse light and converging it down onto one space. Okay? I have an answer.
Okay, so you know how like your
So here we have examples of converging and diverging lenses. Here light is coming in, and this is a convex surface. It has actually two convex surfaces on this particular example. So light comes in, it gets bent and bent again, and focused down to a point. Converging lens. Diverging lens, two concave surfaces, and light comes in and goes whee and gets kicked out and scattered. And so an image here will get projected into a much larger image after the lens. Okay? Converging and diverging lenses. Here's examples again with a series of lasers that makes it easier to see. Here's again a converging lens. All these lines of light that are parallel get focused down to a focal point. And here a bunch of parallel lines of light get scattered. Just another example of that again, a light box projecting 3 lines of light and it gets scattered by this lens. And another example of a converging lens. So you can always tell if the lens will be converging or diverging based on the shape. If it's thicker in the middle with convex sides, it'll be converging. If it's thinner in the middle with concave sides, then it'll be diverging. Okay? I say 3 common uses, and yet look, there's 4. Oh, I get it. Number 3, common uses. Okay, good. There you go. I thought I was stupid for a minute. So I was stupid because I thought I was stupid, but I'm not stupid. Which meant, okay, anyway. Common uses of lenses are for vision correction. As we have said already, that is the most common use of lenses is vision correction. Magnification. Lenses were first made to look at small things. The first lenses made were for microscopy, to look at little tiny animals in the water that people called animalculae. Little itsy bitsy things, we would now call them like bacteria, protists. So the first lenses were made for magnification. Photography also obviously uses lenses to sharpen an image from various distances and put it on a film or on a digital capturer. And then fiber optics, as we've already talked about, refraction is used in fiber optics to keep a light signal inside a glass wire and let that light signal travel for a long ways with great fidelity. So there you go. Any questions?
Nope.
Alrighty, I think I might have one more picture and then we're done. No, we're just done. There you go.